Hello, my name is Aydın Alatan. We will have the EE584 machine vision course this semester. Now, machine vision is a very important field. About a few weeks ago, uh, there was an article in Forbes magazine, only a few weeks ago. Okay, as you can see here, the date is like this. It's told that $1 billion vision-based startups is expected. And it is said computer vision, it is denoted as the most technologically mature field in modern artificial intelligence. Okay. Now, I'm talking about something really important, not as a scientific point of view, but also uh, turning the technological concepts into uh, the human beings as their own good, it's also nowadays available. Therefore, I'm not talking about something futuristic. Nowadays, all these things that I'm going to talk about in this course will be available and will affect our, maybe will affect our daily lives. Okay. Now, this course is, I conduct the course in four main parts. The first one is image formation. Okay. We will try to learn how an image is formed so that looking to an image, we can analyze the scene, everything, determining the image better. Okay, therefore, we will first understand how an image forms so that we can go back and understand the scene, everything about the scene from an image easily. The second thing will be early vision. Okay, early vision is a little bit fundamental concepts like binary image analysis, dealing with the masks, which is also very important, and also the edge detection, feature extraction, obtaining corners, edges, which are really important representations that summarize important uh, concepts in a scene. And finally, I'm going to talk about optic flow, which is the most fundamental information about consecutive images. Then we will go to a higher an upper level, which is called the mid-level vision. Okay, that will be about segmentation, where we will see thresholds that determining making some decisions. That's why we call it mid-level. There will be models, not simple signals and their processing. There will be probabilistic or graph theoretic models that will determine the relations between pixels. That's why we call it mid-level vision. Then afterwards, the mid-level vision will be segmentation, tracking, not optic flow consecutive two frames, but for a long sequence of time following the scene and objects, and also structure from motion. In other words, geometrical modeling of the scene, the points, their projections, then trying to reconstruct back this 3D scene. This is inside the mid-level vision. And the final thing will be, obviously everyone is expecting high level, but I call it learning based as well. Let's call it high level or learning based. Okay. And all these information here in these uh, newspapers or magazines, all the hype that we are talking about is about these new learning-based high-level vision techniques. Okay, until now, in the last 30 years, maybe people, the scientists, try to solve these problems by their mathematical formulations or trying to come up with some handcrafted results by their experience or modelings. But nowadays, the problems are solved by giving some input data and trying to obtain this output from some given ground truth labels, either a segmentation of the masks of an object or optic flow field. And the black boxes are basically estimating those results through a learning process. Yes, these are very powerful, successful, and we will see in this course. Now let's start the first part, the image formation. And as I've said, we will talk about projections, brightness. This video will be until here, I believe. And then the next video, I'm talking about lenses and image sensing. Okay, first of all, let's understand the concept. Vision is the most powerful sense, and as according to the Forbes magazine, it's very, very important nowadays for everyone, and most complicated as well. We are doing many things by eye, vision, as human beings, but also very difficult to understand. Nowadays, people maybe don't care about the how it's being formed or obtained, but rather people are just nowadays just imitating the human neural system by giving some training information and making a learning of these algorithms without caring about how the real human vision system works. By the way, we are trying to obtain a description, a symbolic description, and it's from the images. For example, we are not talking about audio in this course. We are not talking about anything else. This course is about images. Okay. Therefore, we will talk about images and we will obtain descriptions. This is not image processing. Okay. Image processing is somewhat different. Image processing means you get some image and you process it and you obtain another image, like a noise removal or enhancement. These things are image processing, okay? Therefore, in the meantime, pattern recognition is about not images, by anything, any kind of vectors, data that we have to use we have to classify or describe or whatever we do. This course is about only images, but it's not about processing of the images, okay? Therefore, computer vision, machine vision, and image processing. The name of the course is machine vision, computer vision. They are really relevant, to tell the truth. There is a very small distinct difference between them. I'm going to just tell it shortly. In fact, I don't care about either machine vision or computer vision. Machine vision means more uh, constraint on the environment, the light, everything is known, you fix them and you do many things in a more controlled way, in a factory or in a laboratory. Computer vision is more general, and from an internet you don't know who captured the video, and you basically try to obtain those results. Therefore, these two terms can be used interchangeably. Okay, there is no problem with telling computer vision or machine vision. Machine vision is more controlled. That's the only thing. But for example, in this course, I will talk about computer vision. I'm going to talk simply about vision, okay, rather than computer, machine, or robot vision. Now, once again, descriptions from images. Image processing gives you processed images. Pattern recognition takes some representations, features, makes some decisions maybe, okay? What we are doing is we are maybe doing all these things together, okay? There will be an image and I will have to make a decision at the end, or I will convert into a form so that making a decision is much, much easier, okay? Therefore, I'm talking about this problem, and let's understand we are talking different from image processing, pattern recognition, and vision is something general, either machine or computer, it doesn't matter. Okay, now image formation. The main problem in this chapter I'm going to talk about. And what is image formation? There is an image from from a satellite or aerial image over there. People are just standing somewhere with some different clothes on top of it, and then you see a silhouette of a lady, the red lips and whatever eyes. This is an image formation. Therefore, how do we form an image? Once again, the reason why we are learning this chapter is Learning this chapter will help us uh, going back from the images to the real scene. We are always interested about the scene that we are capturing. Therefore, we are capturing a surveillance camera or a satellite image, whatever. At the end, whatever we are looking at in the image, we are interested inside the scene. Going back to scene is only possible when you understand how you form an image from the scene, from the light, from the camera system, and then you will be able to go back. Okay, the first thing is there is a 3D world that we are interested, and during image formation, it maps onto the 2D image plane, and two crucial questions that in our minds: position, oops, I'm sorry, position of the 3D object, where will it be on the image plane? I have a 3D point here. It goes to a pixel on the image, how it's determined. The second thing is brightness. There is a black or a red light. It goes there. How will be the pixel value? Okay, therefore the number that you obtain at that location. Therefore, again, on the images, this time we are going forward. We are going forward, and there is a scene creating an image. How these things are formed. Knowing these things, I will know how to understand the scene better. Now, the pinhole camera model. Okay. Now, about the pinhole camera model, let's first of all look what it is. It's a very old concept. People are doing these things for a long time. If you have a chamber, a room, only a single point here, and if you have relatively a bright surface, reflective, bright white surface here, people know for a long, long time on this wall, you will be the reverse replica of the scene that you observe outside. And still, there are in some science museums something called cam. They call it uh, uh, camera obscura or something like this. Okay, that's Italian word, I think. Therefore, it is just this idea. You go to a dark room and there's a little hole somewhere in the room and you see the outside. Okay, there are many those kind of interesting things. This is the fundamental concept of our conventional cameras as well. This is called pinhole. There is a little hole, very small hole, which is creating the scene on a surface. If that surface is capable of capturing, storing the visual information by somehow, due to chemical substances or due to some microelectronics or photonics devices, it's capable of capturing it, then you formed your image. Okay. Now let's see what we are talking about here. This is our pinhole. There's a scene. As you can see, if this ray, this light ray, going as uh, in a single directional, okay, passing through here. Therefore, that point A will be here, B will be here, and whatever C will be here. Oops, this is B. Sorry, C will be here. Therefore, as you can see, assuming that light is propagating in a single direction, okay, uh, we will assume that the reverse replica of the scene will be obtained. And obviously, by using very simple trigonometry, using some equal triangles here and here, these angles are equal to each other, kind of, you will be see that we can talk about if this distance is known in 3D, I have to know this distance by the help of this parameter and this parameter as well. These are very simple equal or similar triangle concepts in trigonometry. Therefore, I'm talking about the very same thing. Maybe a little thing to note again. Sometimes it's difficult to work with the real life, which is really the boxes here, and you are having this camera obscura, and on the wall you see the image. But how about putting the same distance, a virtual image plane here? This wall is like that, and the beautiful part is this virtual thing, nothing is reversed, and the same geometric rules are applied. Okay, if this is 5 meter, if this is 5 centimeter, this is also 5 centimeter kind of. Okay, therefore we are simplifying our mathematical modeling. This is the first model that we see in this course. Okay, now this is our object here, x, y, z, capital X, capital Y, sorry, capital X, capital Y, capital Z, and this is the pinhole. The real thing is behind, but for simplicity, we put it in front. And this is F, whatever the name, maybe what is this little F here? There will be a meaning shortly for this F. That is the distance of the this point and the virtual image plane or back plane that we have in the conventional camera. Okay, this is your F. Now, this F is basically due to this similar triangles, that distance becomes obtained like this. Okay, therefore, this thing, the ratio of this one to this one should be the ratio of this one to F, which means that distance is equal to F over Y times Z. This is a very, very simple formula, but that is the fundamental formula of your mobile phone cameras or everything. Okay, therefore, this is simple. The only thing is there could be maybe something is dividing something. We don't like divisions in practice because if we want to go from these pixel values back to here, divisions, unknowns become difficult for us. But nevertheless, simple formula, we are very happy, which is saying that your x distance with respect to this coordinate system, the origin is here, okay, and the y and the z, their ratios gives us nothing but the pixel positions. Okay, now in practice, really the cameras that we also work or use work with this pinhole concept. Hey, there are lenses over there. Okay, we will come to that later. But at least about 150 years ago, people are just opening a box. There was a little pinhole over there. They close it in a few seconds, maybe more than that. Then captures the chemical substance. The light is coming from the scene. Therefore, really, the camera means pinhole. Therefore, these geometric relations are valid. Now here, if this is our pinhole here, and then there are these three scenes, the poles, okay? These like lamp poles, okay? We have like lamp poles here. This is A, B, and C. These are in the same distances, 2D far away from this pinhole. This is 1D far away. These are with the same height, 5 meters, 5 meters maybe. This is 10 meters maybe, okay? Let's assume. There are A and B are two different heights, but they are in the same distance far away from us. And A and C are, they have the same height, but C is much nearer to us. Now, what is the observation that we see if we go, as we did before, this point goes to this point. This point goes to this point. That point goes to that point. Goes on like this. Okay, this point goes to this point, and finally that point goes to here and here. Okay. Now, as you can see, we have this, and what do we see in our image at the end? We are dividing by the z to obtain those lengths. That was 10 meters, but you divide it by 2d. But there is also 5 meters, you are dividing by d. Therefore, what you are having is this point, the C length, the C, maybe let's call it 10 pixels here. And this guy, the tall guy, typically 10 meters over there, but also 10 pixels here. they have the same pixel value. How it's possible? Because it was far away. The far away concepts are getting smaller. Why? Because pinhole cameras do that. In our eyes, that's the same thing as well. But mathematically, I just showed that these kind of little tricks, uh, two d far away, twice height, they will observe at the same time. We are in other words, if we close our single one eye, when we look at the 3D scene, there could be really a little bit different perceptions. There are some street arts, you know it, okay, they draw something, when you look at it, it looks like a 3D concept. Or for example, here, if I'm not wrong, there was a video, you can look at it by yourself. It looks as if there is a typical living room, but the trick is this is in front of the lens, that is in front of the lens, and also there was something else, okay, there, if I'm not wrong, these are also some tricks. I mean, these things are due to you are losing information because you divide your two numbers and obtaining a single number. And obviously this is the reasons of having some little perception misleadings. That's also showing us how it will be difficult from observed pixel locations going back and obtaining the 3D scene information. That will not be trivial, okay? That's a little, in fact, clue here. We are losing information, therefore we could have problems while we are going back from pixel positions to the real 3D points, coordinates. Okay, these are all these tricks, all based on the fact that uh, although this is something drawn, and if you look from only from this angle, you will see like something 3D visual perceived. Our eyes are basically deceived, but these are all due to we are losing some information. Okay, like parallel lines meet, as you all know, when you look at images, the railways are going and connecting to each other. Therefore, if you have like these are parallel, if this is the real thing, and then you project it to here, this is our virtual plane, you go there, and this is the same road. This road is this road, and it's connecting to here. Okay, in infinity they just meet at infinity, but parallel lines in real life they don't. But effectively in this kind of pinhole camera projections they meet. Okay, now let's give a name to it. Let's give a name to it. It is called perspective projection. Okay, perspective projection is this, which is obtained for modeling pinhole cameras, and it is being used, okay, in real life. All the cameras lenses are based on this idea, but sometimes we make some approximations. Okay, approximations. Why approximating it? Because the scene is in a different way. Why should I care with this relatively complicated nonlinear numbers? If they are unknowns, these are unknowns. The unknowns are dividing each other. These are nonlinear things. We don't like them. We make approximations. These approximations to the perspective projection. Perspective projection is perfect. Approximations are not exact, okay? Therefore, which is the first one is called affine, weak perspective, and orthographic. I'm going to talk about them one by one. If you look at a wall, just the wall behind me, from your camera image plane, they are just parallel. The virtual plane of the camera and the walls are parallel. You don't have to care about these kind of things. I'm going to show it. Weak perspective is you are in a satellite. There is a relatively very beautiful field. It's almost constant, not constant, but almost constant. Then it is called weak perspective. I can do a little trick over there and approximate. The scene is approximated. as a plane, and we continue. Orthographic is you are doing too much approximation, and as if you have a focal length like infinity, and then you have those cases you have orthographic. Now let's go one by one. The affine. This is pinhole. This is image plane, sensor, whatever the chemical substance, good old films. This is your scene. This is scene. This is real life. The wall behind me. Okay, it's almost my camera and the wall is like their sensor and it's not parallel. Now, therefore, all the things on the wall, this point P, this point Q, they are all constant distances called Z0. And then let's apply, first things first, our fundamental perspective pinhole camera projection by putting a Z0 every time. Every point, P, Q, whatever. You don't see anything else. This is a scene consisting of a plane. Therefore, everything is Z0 distance away. Hence, dividing F by Z0 will give you, if we define it by M, and this thing will be equal to x times, x is equal to m times x. There is a minus sign, maybe you don't like this, but this is due to this flipping operation. Therefore, if this is your coordinate system, okay, if this is your coordinate system like this, I, J, K, okay, X, Y, Z, whatever. And if this is positive, obviously, this is negative. Therefore, I mean, sometimes we don't care about these things. Sometimes we talk about our virtual image planes, then you don't talk about these things. But I mean, if you put your coordinate system in this way and you really use the image plane, then you have to put a minus sign here. If you assume a virtual image plane, which is the same distance from the f distance from the origin or the pinhole, then you will don't have to have this x minus. That's not something important for us. Okay, at the end, I got this result. Your 3D point x and your 3D coordinate y. Multiply with a constant number and you obtain x and y. That's beautiful. Okay, that's because constant, your f is constant, z0 is constant. You will just deal with this. Therefore, looking to the pixel, xy coordinates, hey, there is a MATLAB xy here. That xy will be nothing but capital XY directly. Okay. What is a little, and you know also the z distance, hopefully, and you will have everything available. Therefore, a affine projection, if you have this scenario in your scene, why not use an affine transformation? Three perspective is this. Life is not as like this wall. Even this wall, you see there are two, no, sorry, there is over there this differences, for example, between two planes in the wall. Therefore, there could be a delta z, and all the points P, Q, R, S, all of them are inside, between these volume. Okay, it's inside this volume, and that delta z is relatively okay, assuming this delta z and everything is inside here, okay, all these points you are in the scene are inside here. You first look this thing. Obviously, you will again write a z0. You will write z0, but obviously this z0 is the center, maybe this volume center. P, Q, R, S, their z values are not equal to z0. We approximate them to be equal to z0, and therefore we will have approximately this relation, again, approximately equal to m. Hey, when does my approximation is good for me? Well, once you have your delta z, your delta z is much smaller with respect to z0, you were in a satellite 1 kilometer away, not one, everything is 1 kilometer, maybe 100 kilometers away, and you are looking down to Earth and there are 500 meters. Well, that could be a really very weak perspective projection, and you can assume this kind of a relation. Okay, therefore, in real life, everything is not perfect planes like this. Weak perspective will do the job as long as you just check this and your depth range of the scene, the tops, peaks, and the values that of the scene versus the total distance of the scene and the camera is much smaller with respect to the total distance of the camera and the scene, then you can assume weak perspective. Orthographic is uh, you have a scene depth range is very small with respect to depth, and the camera distance remain constant. For all your images, you have the same constant. Therefore, that this Z0 is constant. Okay. Therefore, you have this kind of a relation. Choosing m is equal to -1, you obtain such a very, very simple relation. Okay. That simple relation simply says you have uh, you have a pinhole system, but they are really far away from each other. It's like infinity here. Hence, you have parallel lines, and this capital XP goes to small xp. They're equal. Capital YP is going to small yp. Okay, therefore, you are talking about this, and that ZP is a Z0, which is constant and which is much larger with respect to your depth range. Okay, if this is the case, this is an orthographic projection. Orthographic projection is not very practical. There are not orthographic cameras in life, but sometimes you would like to have virtual cameras work like with orthographic projection, like remote sensing. You would like from the top looking to a, for example, a map. Okay, therefore for those cases you prefer to have as if the scene is obtained through orthographic projection. This is a very rough approximation, but again, for some cases, some scenarios, it could be useful. Now, summary is perspective is the real thing, and this is the formula, and you should know this formula very well in this course. Orthographic is this very simple formula, and obviously this is not memorial, it's a realistic projection. This is the projection, okay, not realistic. This is the projection of pinhole camera, and if the depth range is small and constant Z0 here, orthographic is also a good approximation. Okay, therefore these are our concepts. Now, before going to the brightness, let's stop here and let's leave the brightness and all the other things into the next video.